welcome back to the show that tells you you are a quantum computer with free will, integrating information into a unified experience. My name is Justin Riddle, and this is episode 33 of the Quantum Consciousness series. In today's episode, I'll be presenting an interview I conducted with Kelvin McQueen, a professor of philosophy at Chapman University. This interview took place on November 6, 2022 in Orange, California. In this interview, we talk about the measurement problem in quantum mechanics, integrated information theory and the updated quantum integrated information theory, and a new model for how consciousness might collapse the wave function that was developed with Kelvin McQueen and David Chalmers. Now, I'll be interrupting this interview periodically to provide a bit of additional context to these ideas and my own take. This episode is available on YouTube, and an audio-only version is available on Spotify and Apple Podcast. If you like what you hear today, please like this video, subscribe to this channel, leave a comment below, or for the audio listener, write a review. And without further ado, let's hop into the interview.
Join me deep inside the mystery of numbers. Hameroff of metaphysical new. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
All right, I'm sitting here with Kelvin McQueen. It's a great pleasure to be here with you.
Great to be here.
Yeah, Kelvin is working with David Chalmers on a theory of how consciousness collapses the wave function. So yeah, I really want to, first introduce yourself, and then I just really want to hear more about this theory.
Sure. I'm Kelvin McQueen. I'm a professor of philosophy at Chapman University in California. I work in the philosophy of physics, especially interpretations of quantum mechanics, and also philosophy of mind, where I'm really interested in the theories of consciousness. And sometimes I combine the two topics, as in this theory.
Nice, very nice. So I know you just had a paper come out. It was published as a chapter in a book, right? So This is your new theory. Yeah, do you want to just give us an introduction? Where do we begin?
The paper is called Consciousness and the Collapse of the Wave Function. It is trying to develop a theory that was put forward, primarily it's associated with Eugene Wigner in the late 60s, this idea that consciousness causes the collapse of the wave function. So maybe it's worth saying something about just wave function collapse and where that comes from. So you start with the measurement problem. Fundamentally, this is meant to be a solution to the measurement problem in quantum mechanics. So what's the measurement problem? Well, open up a textbook of quantum mechanics, the sorts of things that you learn if you take a undergraduate class in quantum mechanics at university, and try and figure out what it's telling you about reality. Try and figure out what its laws of nature are and what it says about physical systems. And if you just take a literal reading of it, it looks like what it's saying is physical systems evolve deterministically in accordance with the Schrödinger equation, except when they're being measured. So if you're not measuring a system, it will evolve deterministically. If you do measure the system, suddenly it acts randomly. So the Schrödinger equation, which is deterministic, no longer applies to the system. Instead, the system seems to collapse and act randomly rather than deterministically. So when does that happen? Under what circumstances does a system stop acting deterministically and start acting randomly? And textbook quantum mechanics tells us measurement. When the system is measured, that's when it suddenly acts randomly and not deterministically. And the textbook doesn't tell us anything more about what it means by measurement. And that's the measurement problem. How to complete this theory, to remove this vague word measurement, which is playing such a fundamental role. So Eugene Wigner's suggestion was sort of pretty straightforward. Just take the textbook literally, but replace the word measurement with consciousness. So now consciousness is what's causing the collapse of the wave function. But the problem with that, the immediate problem with that is it's a little bit unclear how it helps. You might think the word consciousness is just as vague and obscure as the word measurement. So now we've solved the measurement problem by replacing one obscure notion with another obscure notion, and we haven't really gotten anywhere. And so for that reason, and for other reasons, such as it looks like a dualist theory, and that's an unpopular view nowadays, this has been largely dismissed. Mm-hmm. But the objection that consciousness is too vague or obscure to enter into a physical theory like this looks like it may no longer hold up. And that's because, for example, of the integrated information theory. Here we have a theory of consciousness that tries to be mathematically precise, tries to represent consciousness as a measurable quantity, which you can model mathematically. And now all of a sudden, you've got to look a little bit different at the consciousness causes collapse hypothesis. It looks like the objection that consciousness is too vague doesn't fly anymore. So our project was really about how can you come up with a precise, mathematically precise model that entails this consciousness collapse idea that is also experimentally testable. The testability is certainly one of the big things driving me. And the idea, the hope was that IIT might be able to get us there. Integrated information theory might be the key to at least get us a first initial consciousness collapse model that is precise and that is testable.
Yeah, great. So I think, this begs the question, what is IIT? How would you define it? I know IIT often is simultaneously met with a lot of fascination and a lot of intrigue. And I know a lot of people personally that are big proponents, but simultaneously it seems very convoluted, technical. Is there a way that you can really break down the metaphors at play here? And how do we sort of wrap our heads around integrated information?
Yeah, let me do my best. So the starting point is just phenomenology. The starting point is introspection. Introspect on your conscious experience and try and identify something very unique and distinctive about conscious experience that you can then use to develop your theory of consciousness. And of course, integrated information is the sort of key thing that the integrated information theorists put their finger on. What does that mean, though? How can we relate that just to ordinary conscious experience? Well, the first thing to note is that your conscious experience encodes or contains information. Your experiences are informative. Your experiences represent, your visual field represents the world as having certain features, colors, and so forth. So there's information encoded in your experience. So the really key point is this integrated part. So the idea is that the information in your experience is taking a form that's very different from the way you find information encoded in other informational states. So what's really unique here? Simplest example, imagine a blue ball. You observe the blue ball, so you have a visual experience as of a blue ball. And so the experience encodes information. It contains the information that the ball is blue. It contains information that it's spherical. It's got a spherical shape. What seems distinctive about the information in the visual field here is that the bit of your experience that gives you the information that it's blue is also the same bit of information, the same bit of the experience that gives you the information that it's spherical. After all, if you try to delete the blue from your experience, you would thereby delete the shape, the sphericality. And that's interesting and distinctive. It's like, you think of any other informational states, like your beliefs. You believe that the ball is blue, you believe that it's spherical. These seem separable, these beliefs. You can write these beliefs down as a conjunction of beliefs. I mean, it seems separable. It seems, in a sense, not integrated. I also like a thought experiment that goes back to Frank Jackson, who was talking about integrated information, actually a long time before the integrated information theorists. And his example is, imagine that you're reading a newspaper. You're reading about a sports event in a newspaper. Maybe it's a soccer game, and so you're reading about the winning goal. Now imagine you're imagining the scenario of the soccer player scoring this goal. So you're sort of translating information in a newspaper to information contained in your imagination, because you're imagining the actual event. And just notice the difference. So when you form the experience in your imagination of this event, you've got to fill out a lot of details that aren't there. And for example, the information that gives you, the color of the t-shirt of the soccer player is also going to be the information that gives you the location of the soccer player. So it's just more examples of this integrated aspect of the experience. But then you go back to the newspaper clipping. These are all separable pieces of information. The soccer player was this far away from the soccer goal. The soccer player was wearing this t-shirt. He was on this team. It's all separate. But then in your experience, this information comes together in this very fused way. So we call that integrated information. So that, I think, is the starting point of the integrated information theory. And then I think the next point, which is, it's a little more abstract, but what you're trying to do is you're assuming that there's a tight connection between the physical state of your brain and your state of consciousness. So you're thinking that if these are really essential parts of your conscious experience, something in the brain should reflect that. So something in the brain should reflect the integrated information encoded in your experience. And I think much of what IIT tries to do is it tries to figure out a way of modeling integrated information in the brain that corresponds to integrated information in experience. And the idea of integrated information that the theorists have come up with, I mean, I would say kind of vaguely related to the integrated information in experience that I just explained. I would not go so far as to say you can deduce the physical model of integrated information from the phenomenological idea. But I take it the whole idea of IIT, I think the best way of looking at it is you're just doing the best you can. You've got to come up with some measure of integrated information in the brain. It might not look exactly like integrated information as brought out in this intuition, but you have that as your proposal, then hopefully you can test it, you can refine it, you can go back to it, try and make it look more like the intuitive notion if you like. But that's, I think, the starting point for me.
Yeah, really interesting. Yeah, I've also heard like Tononi describe this as an intuition, and integrated information is maybe fundamentally this intuition, this sense of what we're trying to describe. And has the mathematics changed? I know there's like version 1, version 2, version 3, maybe version 4. Is that kind of, different math to try to get at this fundamental intuition? Is that how you view that? Or
yeah, I think the evolution in the math is a few different things. One is to try and capture the intuitive concept. But then also IIT is meant to apply to everything. It's meant to give you an algorithm. You give the algorithm the details of a physical system. The algorithm outputs the amount of consciousness of the system. So in principle, you want to be able to give the algorithm any physical system. But right now it's pretty limited. It's limited to classical. Well, it's been generalized to the quantum realm, which we might discuss in a moment. But limited to basic classical networks, discrete physical systems that you can break down into a network that has nodes, connections. Part of the goal is not just to capture the intuitions, but also to develop the mathematics so that it applies to a wider range of physical systems.
Gotcha, because it seems to me like fundamentally connectivity really is the core component of IIT. And I guess it's describing like sort of this graph theoretic metric of an interconnected system of units. But it really seems like connectivity is like the fundamental mechanism sort of at play underlying how information is passed around, and that passing of information between units. And then once you hit a point where you can't separate the network out, now you have something that's integrated.
Yeah, you're right. You need a system that looks a little bit like that. It has nodes and it has connections, because after all, when you're figuring out the integrated information in the physical sense, you're asking, well, how much information does the state have about the next state that it will be in? And that gives you, how predictive is it of that next state? And that gives you your measure of information. But then to get the integrated information, you then ask, well, how much of that information is lost by cutting connections in the system? And that's going to give you your measure of integrated information. But of course, you need connections in the system to cut in the first place to make any sense of that. And it's just not immediately clear at all how to apply that to certain physical systems, continuous systems. Think of the ocean or just a lake, just a puddle of water. How do I calculate the integrated information of that? What are my connections between my nodes? You can try to sort of discretize it and think of
every single molecule in the whole lake.
But you've got to look at it at different scales. So you can look at it at the scale of molecules, but then you've got to look at the different scales, just like you do with the brain. You look at the scale of collections of neurons, individual neurons, and then what's going on inside the neurons. I don't know, maybe with a lake you can stop at the H2O molecules because maybe it gets too continuous after that. But that's not really built into the theory, but that's things that need to be clarified by the theory, by future versions of the theory.
Totally. I mean, this is a bit of a tangent, but when I think about IIT, I think that is a big question, right? How do we define our units? Often it's just default, neurons are the unit of the brain. But as a cognitive neuroscientist studying humans myself, I mean, I operate in like cortical columns and regions, these more macro systems, and they don't always have like a clear anatomical boundary.
Right.
It is kind of interesting to kind of think, where can we or should we apply, these metrics?
Yeah.
Is it inappropriate at like the scale of entire brain regions.
Yeah, absolutely.
Yeah.
You need basic building blocks. You need the elementary particles that compose your system, and then you can start composing them into composite objects. And so you can start talking about parts at every level in that way. But especially if your fundamental level doesn't have components, doesn't have parts, doesn't have particles, but is, say, a continuum, like you do get in some physical theories where at bottom you have a continuous field. With values that fluctuate, but there's no actual dividing, then it's a little bit hard to see how to apply this theory.
And thinking about electric fields in the brain, right? If they are kind of fundamentally delocalized, where like regions are blurring into each other and you're struggling to like cut it up into units. I mean, I think the cell is clearly a unit and we can all kind of agree on that. So yeah, maybe that is just the most straightforward way to apply the theory, but yeah, it'd be cool to hear, I don't know, new ways of applying it to different systems. All right, so let's chat about integrated information theory real briefly, and I'll set up a little bit more of the intuition than what we covered in the interview just now. So integrated information theory really is the mainstream accepted model for how consciousness arises. So if you went to a conference, to any neuroscience department or philosophy department, you can get a lot of traction, and it's kind of accepted that if you're a proponent of integrated information theory, this is sort of like a safe opinion to have, which has a lot of, in my opinion, overly simplified way of looking at the brain, but there's some good intuition behind it. And so you can kind of scoot on by claiming this theory, and you can go relatively unchallenged in this belief. So first I want to lay out, what is integrated information theory? And fundamentally, let's just look at the words, right? Information, content, it's a computer metaphor, right? This is a digital computational metaphor where we're saying there's this binarization, some physical state, some representation, ties in nicely with modern technology. Information is a part of our experience. There's the content of our experience. The second part here is integrated, right? And we have this naive, sort of intrinsic experience of being a single self. I identify as Justin, you identify as yourself. So we're kind of tapping into this feeling of being a whole person. So integrated information is saying that there is a content to our experience. We're capitalizing on this digital computer metaphor of the mind. And then we're acknowledging the kind of weird aspect of ourselves where we feel like we are a single self. And one of the major challenges in neuroscience is to create a unified experience from the brain, right? You have all these neurons, all these cells, all these proteins within every cell. How do you create anything that looks remotely like a single person? So to go through Giulio Tononi's 5 axioms for integrated information theory, the first one, information, we talked about that. Integration, the idea that we're taking this information and packaging it together. And an important thing that he uses to define integration is that this is sort of the set of nodes and their connections and their influence on each other that is maximally irreducible. So this is sort of the biggest chunk in your system where you can't break it up into its component parts, right? And this is this whole, the whole is greater than the sum of its parts intuition, where if we can cut something out of the system and there's only a minimal disruption to the whole, then it wasn't really fully integrated into that system. So essentially, we're presupposing that there's this integration and we're trying to define some constraints on what it means to be integrated. And essentially, that's what this theory comes down to. 3 more axioms. Intrinsic existence. So this is a bit hard to find like a clear definition, but essentially it can be viewed as kind of a type of reductionism where once we define the mechanisms for this integration, that is one-to-one our experience of who we are. So we're trying to capture subjectivity, this intrinsic nature about us, and we're trying to say that it exists in some way in the brain in this physical system. So intrinsic existence means we're going to find it somewhere in there, and that is going to be one-to-one mapping how we are, who we are. All right, so the next axiom is compositionality. And essentially what this is, and it gets a little vague, it is sort of the space of that system. So if we kind of define the system as a bunch of nodes and edges, and they're all interacting with each other, this system as a whole, if we just assign values to all these connections, to all of these nodes, we assign a bunch of values, there's some space that we could define, and that space would have some sort of composition. So as the system evolves, all these numbers are changing. Every node, let's say, has a number. Every connection has some number. As these numbers are changing, we could plot it, and there's this version and that version. And because it gets so complex, this is a very large multidimensional space, but you would have one specific composition associated with one conscious experience, and then this other setup would be a different conscious experience. And this is what Tononi defines as qualia space. There's sort of this space, and we're just going to make this intrinsic one-to-one mapping between conscious experience and some layout of all these nodes and connections. And then there's that composition, there's another composition, and that is the qualia, the meaning, the feeling of that moment, of that experience. And then the fifth principle, which I think is probably the weakest, most magical part of this theory, is exclusion. And this is really fumbling at trying to create a single exclusive conscious experience out of this network. All right, so let's dive into that a little bit more. So what is sort of assumed in integrated information theory is that we need to define a bunch of nodes and then a bunch of connections between these nodes, right? And so the sort of default assumption, and I think a lot of people just take this at face value, is that, oh, of course, neurons are your units of the brain and of conscious experience, right? So we're going to take a bunch of neurons. These are your nodes. And then, hey, they have synapses with each other. They have projections and, chemical transmissions between different nodes or different neurons. So the nodes have edges, and we can essentially assemble a graph of the brain made out of neurons as nodes and then their synaptic connections with each other as the edges. And this is the same, intuition behind like a neural network. Is we're kind of taking something that's biologically plausible, we're taking these nodes and these edges, and then we can kind of abstract away from that and just view it sort of mathematically. All right, so what do we define as integration? Essentially, he defines this as some sort of, recurrent feedback loop between two different nodes. So what we want to define is, what does this network look like? And we have the past predicting the next step in time. And we want to see how much of the network is required to predict the next step in time. So as we look at this sort of temporal dependency between time one and time two, we're basically asking the question, how much is one step predicting the next? And what can we remove from the network and maintain as much information as we can? And so the simplest unit that they define is there's two nodes and they both have a connection onto each other. There's sort of this recurrent feedback loop between two nodes. So one is causing the other is causing the other. And so they both have a causal influence where the future of neuron B is predicted from neuron A, and the future of neuron A is predicted from neuron B. If A just caused B, then it wouldn't be as densely integrated, and so there would be lower levels of connection here. So they propose what's called phi, or this integrated information quantity or metric, and essentially this is a metric for how integrated is this system. And so the most minimally integrated information is these two units causing each other, and this would have the lowest phi value, but it would still be a conscious experiencing system. It would just have such minimal complexity. All right, so as we scale this system up into the brain, right, and we have all these 100 billion neurons and all these synaptic connections with each other, clearly there must be this immense complexity within the brain, and so insert complexity, and then we create consciousness, right? So I think there is a little bit of an admission into this sort of complexity fallacy, as I view it, where by definition complexity defies your ability to comprehend what's going on. That is the definition of complexity, beyond your thought. You cannot imagine or picture all the connections. So we have fairly simple units, add complexity, this is our magic, and then we create a conscious experience out of this. So how do we measure the integrated information? So what we want to do is we want to cut this network roughly in half, okay? And let's say, for example, we had two massively interconnected sets of nodes, and then only one or two connections going between these two massive clusters. So what we can do is we can provide a cut to those two weak connections, and now we have two massively different clusters. Essentially what this means is that that was not a very highly integrated system, and so the overall system that includes both of these clusters doesn't have a high phi value because it wasn't very integrated at the end of the day. Now, after we make that cut, maybe we dive into the cluster on the left and we try to cut that one in half, and wow, we really can't find a way to cut this in half. It's so densely interconnected that you have to basically cut, millions of connections, and so it has a very high integrated information value. The problem with this calculation is that it runs into a combinatorics problem, and we covered this in a couple previous episodes, where as you start exploring the space of all possible combinations of different things, you reach this exponentially large space, and it's not feasible to actually search through all these different possibilities. So let's say we have 20 different nodes in this network, and we want to cut it into two groups of 10. There's a huge number of ways that we could subdivide this, and also we need to cut it into 9 and 11, and 8 and 12, and 7 and 13. And in order to calculate true phi, we would have to do all of these different permutations and see how many nodes we could cut away and still maintain most of our information, right? And this is explosively complicated, and there's been a lot of papers trying to figure out kind of heuristics, some hacks of finding a good enough solution for the phi level of a given system. But this is really just like a massive combinatorics problem. It doesn't really speak to the validity of that metric one way or another. It's really just invoking this massive complexity, and in some weird way, it's like hard to even calculate phi. So, it is falsifiable, but there's always going to be some question of, maybe this heuristic way that we decided to make this cut wasn't very perfect. And so if we don't find evidence in support of the theory, it might be that we're using this kind of shortcut and we weren't calculating true phi. So this is maybe like a practical limitation, but it's not necessarily, I think, too destructive to the theory intrinsically. All right, so what are the real problems here? And I'm going to go through a few of these problems as I see it. One, how do we define our nodes? And I talked about this with Kelvin a little bit, but we could define a node as a neuron. We could define it as a population of neurons. We could define it as microtubules, this forbidden structure inside of a cell. We could define it as proteins inside of the cell, right? Where do we actually draw the loop around the node that we're talking about? There's these massive differences in spatial temporal scale, and we need to define the node. Beyond that, let's say we take neurons as our unit. Well, if it's connected by a gap junction and there's electrical transfer between the two neurons, then are they really independent? How much influence do you have to have between these two neurons where they fuse and become a single node. So even a neuron or a cell does have a semi-fuzzy boundary, and there is probably always going to be a challenge in defining what our nodes are, and this theory does not even start to define what the nodes actually are, right? It just kind of takes at face value neurons, neural connections, and there's kind of an implicit assumption that neurons are the units, but it's not even explicated. And then you could imagine spatial temporal scales above and below that might have some meaningful impact on the system, and how are those even being accounted for? Maybe there's a simple way to extend this theory across multiple spatial temporal scales, but who knows? All right, another big challenge here is, what is this information that's being processed, right? And so, we're really banking on this digital computer metaphor. We could, in a very realistic way, think of this as a digital computer where we have one state of time computing the next state in time, and there's some sort of meaningful computation that's being carried out by the system, right? But Scott Aaronson has this really great sort of challenge to IIT where you could define a very, very simple system that is highly, highly integrated, right? But it's computing something extremely simple. So you could design algorithms such that you necessarily need these recurrent feedbacks between all these different nodes, and yet all this feedback is computing something mind-numbingly simple. And so in IIT, there's no sort of framing of what the information processing is, the quality, the type of information that's being processed. And so, I hate to be that guy that brings up Platonic values, but what is the mathematics that are being computed by this system? Is there any sort of differentiation between a system performing optimally, building information, creating new models, new ideas, meaningfully processing information, and then these dummy models that are just computing something extremely mundane, and yet you could make something with a super high phi, measurement, and yet it's got such a higher phi measurement than this other system, except the other system is doing meaningful computations, right? It's processing natural language, it's doing mathematics, it's finding patterns in sensory data. And this could all just be purely digital, right? But IIT does not differentiate the quality, the type of the computation that is being performed, and is there something that you would need to do to account for that? What would you need to change in this theory to make that a part of it? And then on that same end, there's this idea of exclusion, and I really want to hammer this out, because how do we define our nodes, but how do we define our connections, and how do we draw a circle around the system and say this is the system? So within the body, your brain is made of neurons, and yet your spinal cord is also made of neurons, and there's neurons in your stomach. Every one of your major organs has these little nuclei. Do we extend it into the peripheral nervous system? Probably we have to, because it's just neurons connecting all these systems. Tononi makes the argument that you really need a recurrent loop. So he argues that thalamus to cortex and back, you have to have this feedback loop. But if you found the feedback loop in other parts of your body, then that would then have to get roped into the system. And then if we're just speaking very abstractly about information processing, and Tononi and Christoph Koch, who's another author on these IIT papers, they argue for a sort of panpsychist view where you could have a thermostat or a camera or digital electronics that are very simple, and as long as there's some sort of recurrent loops, then it's suddenly conscious. So what prevents you from having a recurrent loop with something from your environment? So you could set up, me and you are having a feedback loop, and you're having a conversation with your friend, and then that feedback loop, why is that not integrating information and extending your brain network into the other person's brain network? And then suddenly you merge consciousnesses and you're just one person. So where is the boundary? Is everything in the system? And is there any sort of limitation on what could or could not be within the system? And then finally, the exclusion principle is the most magical, where even within your brain, you can imagine there's these emergent clusters of highly connected information processing. Are those separate conscious experiencers inside of your brain? The theory argues no. You only have one conscious experience, so the system that has the largest amount of phi, the greatest amount of integrated information, that system becomes the conscious being inside of you, and you are that conscious being. But once again, how do we define the system? And then could I talk to you enough where I knock out your consciousness because we had enough recurrent feedback loops that then my consciousness excluded yours, and you get wiped out and I become the only conscious being in our conversation? Clearly, this seems completely absurd. And so we got to define the system. We need to define the nodes. We need to define the connections. And then now there's this introduction of exclusivity where you need to be shoved, away, and you got to wipe out all these other competing phi clusters, and only one can survive. But then why? Why can only one survive? And how do we define the system in the first place to then start knocking out other bits, right? And I'm sympathetic to the authors. I think this makes sense. We're coming from the intuition, I have a single unified conscious experience. And then we're coming from the scientific side of digital computers, right? Digital computer realm, and we have these different states and these transition probabilities between one state to the next, and they're all causing each other. And we're trying to kind of make sense of our phenomenological experience from within this model. And to me, we're really just trying to shove these two together, right? There's the very safe idea that, you are a digital computer, I am a digital computer. There's nothing controversial here. We're just two digital computers talking to each other. And then now we're trying to make sense of all these, intuitive experiences that we're having from this forced upon, agreed upon model. And I think a big part of this is the challenge of coming out on a limb and asserting that the human mind is a quantum computer, right? It's challenging to think about large-scale quantum mechanical properties in the brain. And so we reject this outright and we just stick to the safe model of you're just a digital computer. So I think a lot of this comes from taking the safe road, which makes sense from an academic perspective where, your reputation is really important. But my opinion out there in the world. I think we need to update for the quantum computer where you have a much more coherent way of creating a single conscious experiencer through entanglement, through the wave function. And we're going to get into those different ideas in the next part of the interview. So let's hop back to it. All right, so let's jump into quantum IIT. And then in so doing, we'll get into this new theory with Chalmers, right? Mm-hmm. All right,
have at it. So quantum integrated information theory is an attempt to extend IIT to a wider range of physical systems. Obviously, in this case, quantum physical systems. Mm-hmm. So it's still very limited. You still need your discrete systems. So you have a discrete network of qubits or QIITs, and they need to be thought of in a network so they can somehow update each other's states overall just by Schrodinger evolution. But there you've got a new network, you've got now a quantum network. And so what you're doing is you're basically trying to just capture the ideas of integrated information theory, IIT 3.0 or 4.0, and just apply the same ideas to the quantum domain. Mm-hmm. Now, I think for the people that were developing this, it was maybe more of a mathematical curiosity. Could you do this? They weren't really sort of trying to extend the theory of consciousness or apply it to consciousness in any way. It was just a mathematical question. Is there objects in quantum theory that can be used just like the objects in ordinary integrated information theory? Are there correlates? And it turns out there is. So for example, you might worry in a quantum system where there's a lot of entanglement, what would your parts be? What would your nodes be? What would your objects be? Mm-hmm. But it turns out that you can represent the parts of a system even when the system is very entangled in terms of reduced density operators. So reduced density operators will replace the classical probability distributions that you find in orthodox integrated information theory. So it looks like it can be done. Mm-hmm. And so that's good. So that's good for us, Dave and I, when we were thinking about this consciousness collapse theory, because we want to make this rigorous and testable. But to do that, you need to take the mathematical formalism of quantum mechanics and then input the relevant values from integrated information theory. Well, you can't do that with IIT 3.0, but you can if you move to quantum integrated information theory, suddenly it looks like you've got the right vocabulary, and it looks like you can perhaps actually construct a dynamical equation of motion.
Yeah, interesting. Yeah, I think one of the appeals of like quantum consciousness theories is that because you have this wave function, which is sort of delocalized, it's hard to decompose it into parts. It kind of provides that holistic entity or like that holistic object unit that can be created from these pieces. And I see a lot of similarity with even just like original classical IIT. You're trying to form some whole from a bunch of parts. And so I think, me being enthusiastic about quantum consciousness theories, it seems to be using a very similar metaphor. And then, quantum IIT almost appears to be like a direct way of trying to calculate maybe the degree of entanglement within a system, or the degree to which the system as a whole is guiding the expression of different physical measurements that could be applied to it. Is that
roughly? Yeah. You're looking at how predictive a given state is of the next state, and then you're asking, all right, can I still have that predictive power if I start making cuts in the system? So if I start dropping, for example, some of the entanglement correlations, the amount that you do lose when you make a minimal cut, that's your measure of the amount of integrated information.
Gotcha. Yeah, it still feels weird to me to take something that's entangled, where almost by definition it shouldn't be reducible, and then now you're trying to cut entanglement relations. So yeah, you mentioned reduced density operators. I think I just need to look into that more myself. But could you maybe expand on what that looks like, or what that kind
so
of
a reduced
entails?
density operator would just be, it's a way of representing the local properties of a physical system. So you might just have...
like you're just zooming in on one property.
Well, just take two particles, they're quantum entangled, and it looks like, well, maybe you can't describe the parts because it's entangled. However, there is a mathematical object in the theory called a reduced density operator, which gives you the probabilities for the outcomes of measurements on that local system. If you were to do a measurement on this, the reduced density matrix just tells you, just for this one system, here's the probabilities of the outcomes of the measurement. Now, it is an entangled system, so you don't derive the reduced density matrix just from the intrinsic properties of this one object. You actually have to take into account this object. But you can sort of trace out information about this object, and you're left with a reduced density matrix for this one object, and it gives you the sort of local properties, the probabilities of outcomes of measurements just on that single object. So that's the reduced density matrix. And for the quantum integrated information theory, what's good about them is that it gives you the parts, it gives you the nodes of your system.
So in a way, it's kind of like the degree to which the rest of the system is going to measure this, or going to influence the measurement outcome in this one property that you're looking at. And so for any given quantum system, you could have various levels of like degrees of influence that the whole kind of makes on that part.
Right.
And that kind of becomes your cut.
Yeah.
Is like the amount of influence on the probability distribution of this more local.
Yeah, one way of cutting would be like you can compare, for example, if I cut the entanglement connection between these two objects, what difference does that make to the future state of the system? And entanglement correlations do something for the entire system. So if that's one of the things that you cut, how much of a difference does that make to the next state of the system? How predictive the current state is of the next state under Schrodinger dynamics? Yeah.
Cool. Okay, so then, let's bring consciousness into this. So how does the McQueen-Chalmers theory sort of use all of these framings in quantum IIT and then add consciousness into the situation?
Yeah, so go back to the measurement problem. You've got orthodox quantum mechanics, which tells you that physical systems evolve deterministically in accord with the Schrodinger equation, except when they're measured. When they're measured, that's when they act randomly, that's when they collapse. So we're now following Eugene Wigner, replacing the notion of measurement with consciousness. So his idea roughly was something like this. So you're performing a measurement, maybe you've got just a particle in a superposition of being here and being there, and then you've got a measuring device that measures its position. Now, the Schrödinger equation without collapse tells us that when you correlate the state of the measuring device with the state of the particle, the superposition magnifies up into the measuring device. The measuring device evolves into a superposition of detecting the particle here and detecting the particle there. Now, what happens when you look at the measuring device to see maybe there's a screen or something and it tells you what the result is here versus there? What happens to you? Well, again, if there's no collapse just yet because consciousness hasn't come into the picture yet, then it's the Schrödinger equation, same thing. You correlate the state of your brain to the state of the measuring device. So the light reflects off of the measuring device. It's in a superposition of reflecting information about the particle being here versus the particle being there. So then your eyes enter into a quantum superposition of seeing measuring devices with distinct results. Mm-hmm. And then that just keeps going into the brain, and then eventually it gets to the neural correlates of consciousness and should superpose the neural correlates of consciousness. But the neural correlates of consciousness are correlated with consciousness. Consciousness, if it doesn't want to enter into a superposition, if that's a fundamental rule governing consciousness, then consciousness will say, no, I'm not going to superpose. I'm not going to enter into a superposition of consciously experiencing a here result versus a there result. Instead, we're just going to randomly collapse to one of those results. So consciousness will enter into a state of either seeing a here result versus seeing a there result, and then all the other stuff in the physical world that's entangled with the conscious mind at this place, at this time, will then collapse too. And so reality will take on a given definite state and no longer be in this superposition.
Mm-hmm. Yeah, so the idea is that consciousness, when it enters into a system, becomes entangled with it, it's going to reduce all superpositions.
Yeah, that's right. And the problem with Eugene Wigner's suggestion was, well, okay, what do you mean by consciousness? How can we be rigorous about this? How can we test that hypothesis? So no wonder everyone just dismissed the Wigner hypothesis, but with IIT, it looks like maybe you can actually have some rigorous answers to these questions because we've got now treating consciousness as a measurable physical quantity, or at least correlated with something that's a measurable physical quantity, integrated information. And so now we can answer that challenge about consciousness being too vague. So the way that we think about it, we think of, a natural way of thinking about the original idea is consciousness is superposition resistant. It resists entering into a superposition. And instead of the superposition, it responds to impending superposition with the collapse of the wave function. So that's how collapse arises. So now we've got a testable theory about when and where collapse happens, because collapse is testable. It's hard to test, but it's testable. If a system collapses, it makes very distinctive predictions. They might be hard to get at, but they make distinctive predictions. So, now what we're suggesting in this theory is that collapse happens when there is a superposition of integrated information. For example, if we just use this measure of integrated information, a superposition will say, okay, I've put my system into a superposition of phi, or integrated information equals 5 versus phi equals 10. If you can put a system into a superposition of phi, then that's banned, that's disallowed by this theory, or at least it's an unstable physical state. It's going to tend towards collapse. Mm-hmm. So that's the prediction that the theory makes. And so in order to actually test that, the challenge is to try and devise a physical system that somehow actually puts a system into a quantum superposition of integrated information, and then check to see whether that's stable or not. So the way to do the most obvious way to do that, I think, obviously you can think of like double slit experiment. Maybe we can somehow get an object that
pass it through the slit.
Yeah, and somehow like the one going through the left slit has a different amount of integrated information than one going through the right slit. But this is maybe not the best way to go. It's a bit complicated. The most obvious way we think of going is use a quantum computer, because a computer you can design a computer to have a certain amount of integrated information. So the hope then would be, okay, if we know that we can build a computer to have a certain amount of integrated information, maybe we can build a quantum computer to put itself into a superposition of integrated information. So that's our current challenge. How do we build such a circuit? This is something that we're currently working on. So we don't have any definite results just yet. But the basic idea if you think about in integrated information theory, just IIT 3.0, what is the simplest conscious system. And it turns out to be a little feedback dyad, a little two-node system that this one will give its state to the next one and vice versa. And so it's in a feedback loop. And that has, in IIT 3.0, that has 1 unit of integrated information, 1 unit of consciousness. So that looks like the simplest system. So now the challenge is building feedback networks like that in a quantum computer. And that's pretty difficult. That's part of the challenge. I mean, if you look at the quantum computing literature, there's different kinds of feedback you can build into a quantum computer. There's something called measurement-based feedback, where you have your quantum computer, it gives you some output, you then measure the system.
And then based on that,
and then you put that back in. It's not what you want, because then you've sort of already done the collapse. We need the feedback to be happening inside the quantum computer and not as a function of the observer. And there's a way of doing that. There's something called quantum coherent feedback, where you can kind of have a little feedback loop in your quantum computer guided by other things that are pushing the state forward. But that's not enough for us. We want that kind of feedback loop, but in a quantum superposition of some sort. So, for example, a quantum superposition of being in a feedback loop and not being in a feedback loop, or this is where it gets very tricky.
Oh, wow.
And so but if we can build this, then we can make good on this promise that we've got a testable consciousness collapse model.
Yeah, are there any known quantum algorithms that are actively using these feedback systems that are in practice already, or that people have theorized to solve unique problems, or is this kind of a new domain?
As far as we can tell, it's new. We've certainly we've looked. We've been harassing a lot of quantum computing experts to just try and find it. It doesn't look like it's out there, but I'm doing some work at the moment with in Durham from St. Elsom College, where we're trying to figure such a circuit out. But this is very much work in progress.
Cool. Yeah, a couple of follow-up questions. Is there in this this collapse model of a super-resistant consciousness, is there a phi threshold for collapse, or is it 1 unit of phi would be sufficient to cause a collapse? And you were also mentioning superposing different levels of phi together, in a conscious state being superposed. Why would you need different levels, or how does the amount of phi play into the theory?
Yeah. So on the first question about threshold, if you impose a threshold, for example, in order to be conscious, you have to have phi equal to 10 million, right? Now you need a very complex system, and now these experiments start to become just as difficult as experiments that test more orthodox collapse theories. And so the sort of, the nice thing about the consciousness collapse model, which was easier to test than other collapse models, that goes away. So we're using a version of IIT on which there's no threshold. Any non-zero value of phi is going to give you some level of consciousness. I mean, that's sort of the thing that makes the overall model easier to test. If the tests don't come out well, maybe the whole thing's wrong, or maybe the thing that we were doing wrong was not imposing a threshold. But start off with the simpler model that there's consciousness whenever there's non-zero integrated information. Your second question was, why do we need different amounts of integrated information? So importantly, the theory predicts that superpositions of consciousness are unstable. Those are the things that tend to collapse. So to test the theory, we need to create a superposition of consciousness. How do you do that on IIT? Well, there's actually two key concepts in IIT. Phi is one of them. There's another thing called Q-shape. Maybe we can talk about it if we need to, but we can do this in terms of phi. We kind of have to do it in terms of Q-shape to have a fully rigorous theory, but we can think about it in terms of phi for the moment. So what we need is a superposition of consciousness. What that means is the system is in a superposition of different conscious states. We need different conscious states, superposition of those.
Gotcha.
Different phi entails different conscious states. It's not the only way to do it. We can get into the Q-shape stuff if you want. And
I was going to say, because Q-shape is kind of the landscape of what your consciousness looks like or what it feels like.
Yeah.
So if you had two identical Q-shapes, then it would be the same conscious experience.
Right.
And you can't superpose the same thing because it would just be that one thing.
Right. And that's actually why phi is not our criteria for collapse. It's not enough to say, oh, well, these two experiences have different phi, therefore a superposition of them will be unstable. The problem with that model is that what happens if you put a system into a superposition of seeing red and seeing blue? Mm-hmm. That is a consciousness superposition, but there's no reason to think it's a phi superposition. Why would an experience of red have more or less phi than an experience of blue? Mm. And if you don't like the example, surely we can find two experiences that are qualitatively different but quantitatively identical. That is, same amount of phi, but different qualia, different qualitative properties, right? So the problem with doing this consciousness collapse theory in terms of phi, which would make a lot of things so much technically simpler, the problem with it is it seems like you could put a system into a superposition of distinct conscious experiences, but it's not a superposition of phi. Mm-hmm. But then on the phi model, there's no collapse. So now the system just remains in the superposition of consciousness without collapsing. Well, that's not a consciousness collapse model. So if you actually want a consciousness collapse model, you have to move away from the IIT quantity of phi and move into its model of the quality of consciousness, which is what we call Q-shape. Originally, it was called maximally irreducible conceptual structure. Too much of a mouthful. Tononi called it a shape in Q space. So we think it's natural to call it a Q shape. So we call it a Q shape.
To me.
Yeah. So the Q shape is...
So same phi, but different Q shapes, and now you're still superposing.
So now we don't have that problem. If we now have our system that's in a superposition of qualitatively distinct conscious experiences with equal phi, we actually get the collapse.
Yeah.
Because it's Q shape. That is, well, what triggers collapse is a quantum superposition of Q shape.
Gotcha.
Because that's really a quantum superposition of the quality of consciousness, not so much the quantity. And that's then going to be the cause of collapse.
All right, so let's talk about quantum integrated information theory. So essentially what this is we're now replacing the nodes and the connections from classical IIT using digital computers to now replacing it with, you guessed it, quantum computer components. So we have quantum bits now as our nodes. So we have a slightly more rigorously or more directly defined substrate for what our different nodes are. And then the connections between our quantum bits is now entanglement. So when two quantum bits are entangled, they share a single wave function or probability distribution that guides the evolution of both of the quantum bits into the future. And one property of quantum computation is that you can set up systems so that they are irreducible. So after you've sort of mixed these quantum bits in certain ways, one example is a controlled NOT gate. This is a entangling gate. When we talked about this in previous episodes, but after going through an entangling gate, you are not able to decompose the system into two separate units or two separate systems. They're intrinsically linked into one wave function. So for me, and in this series, we've been talking about how the creation of these macro scale wave functions is a nice substrate for consciousness because it gives you a way to, in principle, unify a system, and you increase maximally the computational power of that quantum computer, where to build a very powerful quantum computer, you actually want a single integrated unified wave function composed of many, many quantum bits that are all entangled into one giant wave function. So, hey, guess what? Quantum IIT is tapping into this same exact intuition. What is the minimally, irreducible unit of that quantum system? So can we create a integration metric using phi, using the IIT framework to describe how entangled a quantum computer is? And I think I'm fine with this. I think this makes sense. I think this is using the exact same intuitions that the quantum consciousness enthusiasts have been using previously, but now we layer it with a little bit of mathematics to scare away the people that are kind of only superficially engaging. And this gives us a little bit more credence to basically make a lot of the same claims that quantum consciousness and quantum computer people have been thinking about already anyways. That's not a knock. That's just kind of, I think, a historical context here. But I'm fundamentally on board. Now, I don't understand all of this reduced density operator talk that Kelvin is going into. The idea at a high level is essentially that while the quantum system is irreducible by definition, there are some ways of kind of defining what is the interaction of my measuring device with this part of the quantum system. And I'm going to reduce that density operator that would, essentially cover the entire quantum system. I'm going to reduce it down and just kind of focus on this more local system. And we can see how much of an impact the whole system had or did not have on that more local system. So essentially, this is a way of making our cuts. We're trying to sever entanglement relationships in our quantum computer, and we're seeing how much of an influence those entanglement relationships make on this more small part of the quantum computer interacting with my measuring device. And then we compare that to the whole, and then we can get our phi metric from this. All right, so that is kind of the overall quantum IIT approach, is the same intuition from classical IIT, but now diving into quantum computers. Now, one thing that Kelvin talks about is, once again, the need for a feedback loop. So while in classical computers, it makes sense that you would need to have this feedback loop because otherwise you could just have parallel systems going on their own and they're never interacting, right? But in a quantum computer, the system is intrinsically linked. And because a quantum computer is time reversible, essentially this whole system is evolving with each other. And if you create a true entanglement relationship where it's irreducible, then the whole thing is delivering feedback on itself. And there's sort of, to my understanding, like an intrinsic feedback relationship. So the need to invoke a feedback loop, to me, feels a little bit too much like it feels like a leftover classical metaphor, or like a leftover classical mechanism that we're now trying to push into the quantum computer. And I think even the idea of having a feedback loop in a quantum computer, there's some examples where you would do that. So we've talked previously about the Zeno booster in the quantum counterfactuals or quantum interrogation episode. And there you have a weak interaction with a measurement device, and then the weak result of that measurement is then changing the system and introducing a feedback loop. So, there are some examples where this is useful to have a feedback loop, but it's a feedback loop with a measurement device, not necessarily with the quantum computer itself. So, yeah, I do think this is a new domain. Maybe there's something to it, but you already get your unification via entanglement. So the feedback loop in the classical design is trying to give you a substrate, a mechanism for integration. In quantum computers, the entanglement itself, to my eyes, feels like it's enough to create the unification that you're craving in your consciousness explanation. So maybe we need feedback, maybe we don't. The fact that not very many quantum algorithms currently are using feedback, one, this could be, next generation quantum algorithms find some genuine utility to quantum feedback, and maybe that really is intrinsic to how consciousness or quantum consciousness becomes possible, is through feedback. I mean, maybe there's some nonlinear benefit that we don't fully understand right now. But right now, we have a lot of amazing quantum algorithms that we're working on that don't require feedback. So I'm not fully convinced in the necessity of having feedback. Couple more points here. What is the intuition driving this? The intuition, once again, is that consciousness cannot be superposed because your experience is not superposed right now, right? You have one conscious experience that's happening in this moment, and it's not splitting into multiple conscious experiences. And so that same intuition for why we need integrated information is being used here to say that we have a super resistance. Your consciousness is resistant to going into superposition because it doesn't feel right with our experience. We feel like we're one person and we have one experience. And so a superposition of your mind doesn't feel accurate. And so we're invoking super resistance as a way to counteract this counterintuitive, maybe absurdist, surrealist state if your mind were to genuinely superpose into two different beings or experiences. So that's an interesting intuition here. But here is my problem with this thinking. At the same time, Kelvin is developed with Chalmers and with this guy Johannes Kleiner. They've been working on this idea of continuous spontaneous localization. And so what they're essentially saying is there's the Schrodinger evolution, evolving the wave function out into multiple possibilities. And then there's a collapsed function, which is counteracting that. So there's a growth function and a reduction function, and they're both built into the system. And so the superposition collapser is continuous. So it's not thresholded. It's not spontaneously happening in a moment. It's always happening to some degree. And so, in the Roger Penrose Hameroff model, you reach a threshold and there's an instantaneous reduction. Here, they don't want that instantaneousness. So they have a continuous evolution and a continuous reduction. And these two processes take turns taking over. So you go into the collapse phase, you go into the evolution phase, and you have sort of this dualistic trade-off between the two. And they argue that the force collapsing the wave function is consciousness. And so the amount of integrated information, quantum integrated information within the system is promoting a more rapid or a more dramatic collapse. So as integrated information goes up, the collapse starts to occur. And then I guess when that happens, then the evolution takes over again and you run out of integrated information, and then the evolution takes over. So there's some sort of give and pull here. But then the question is, if your mind is super resistant and we're not going into superposition, there's still this continuous nature where your mind would also be superposing, and then the mind is then counteracting and reducing the evolution. Unless maybe there's some sort of dualistic model here where the mind is always whole and unified and the physical world is the thing evolving, and then the closer it gets to the mind, it starts collapsing the physical world. So the mind is not collapsing, but it kind of exists outside of the physical, and it's a bit of a dualism here where the mind is present, the physical world evolves, and then once it touches the mind, it gets too integrated, it starts to reduce again. So you have sort of this evolution and shrinking process in the physical world with a stable mind interacting with that physical system. So I think you would have to have it sort of outside of the system. If you then put the mind inside the system, then wouldn't the mind then be superposing, and it's always kind of moving towards a collapse, but because it's not like a momentary collapse, then you'd have these transition points where you're still superposed to some degree, right? So yeah, I don't really know how the model accounts for that, but these are sort of the components of the system. So I'll leave it right there, and we're going to go into some different implications in the next part of the interview. Yeah, does this add free will into the picture in any capacity? I know you've done some research on free will, and that seems to be something that drives a lot of consciousness researchers, either the mystery of it. Is there any room for free will with consciousness collapsing the wave function? Do you view this collapse as random, chaotic, like kind of in line with just picking something from a probability distribution, or is there something else going on?
So in the model that we've put forward, in the model that we've developed, we think of the collapse caused by consciousness as you say, just derived from a probability distribution. It is completely random, but nonetheless predictable due to the Born rule, which is the way of predicting the probabilities of outcomes in quantum mechanics. So the model itself doesn't say anything about free will. It's deterministic until consciousness enters the picture, until consciousness enters into a superposition of distinct Q shapes. That then triggers the collapse, but which Q shape you collapse onto, that is, which experience you end up having. Just to use the simple example we had before, when our particle was in a superposition of here and there, we had our measuring device that would tell us whether it's here or there. And when you're looking at the measuring device, if there's no collapse, you enter into a superposition of experiencing a here result and experiencing a there result. So just to use that example, the idea would be, so the superpositions do magnify up to the macro realm in accordance with the Schrodinger equation until you get to the brain, where that would otherwise put your experience into a superposition of experiencing a here result and experiencing a there result. So our model says what state consciousness collapses to, whether it's here or there, is fundamentally random. It's determined by the Born rule. So you could have looked at the original particle and what are the squared amplitudes of the particle being here versus being there. Those are just going to magnify up as well, and those are going to give you the probabilities for your experience collapsing to here versus there. So that's the model that we've put forward. So it doesn't really tell us anything about free will. But if you really believe that you can't make free will compatible with determinism, then there might be something in here for someone. You'd have to develop the theory a little bit, but maybe you could have a theory on which, if you enter into a superposition, if you're trying to figure out, do you want to do action A or action B? Who knows what that is? Choosing Italian for dinner over a Mexican, let's say. But you're deliberating between doing A versus doing B, and you might think, your deliberation is a kind of conscious experience. You're consciously deliberating between A and B. If this somehow puts you into a superposition, or would otherwise put you into a superposition of doing A versus doing B, and the consciousness is sort of picking out which action you actually perform, well, maybe you could say develop the theory a little bit more where, I don't know, your conscious will or your conscious sort of feel as to which one you ultimately really ought to do somehow changes those Born rule predictions and sort of makes the action that you more consciously intend more probable. That would be a way of allowing consciousness here to somehow mess with the Born rule predictions, thereby introducing a kind of agent causal libertarian free will into the picture. So it's possible, but it's not a route that we go down.
Gotcha. Interesting. Yeah, part of that, this deliberation that you kind of invoke, it seems like that is almost somehow like some meta-iterative process where it's sort of like necessarily temporally extended.
Yeah, well, I was thinking, how do you get yourself into a quantum superposition of doing A versus doing B in the first place?
It's almost like within the meta simulation of the mind, or like within the contents of your thoughts, you've created two possibilities versus sort of the more like almost mechanistic collapse reality that we tend to think of.
Yeah. I was sort of thinking of deliberation as sort of this process that maybe gives the brain time to allow a microscopic superposition to magnify up into your deliberation so that you somehow enter into a superposition of doing A and doing B. But then that would be sort of, I've consciously decided to do A and consciously decided to do B. Well, that's a consciousness superposition. So then that has to be broken by the rules of this theory, and then you collapse into just doing one versus the other. But how you actually would get a superposition of different choices just out of the brain is sort of presupposed here, and it's not clear exactly how that can work.
Yeah, very interesting. Yeah, so just to kind of like harp on this intuition here, so kind of underlying this theory is this intuition that your mind, your experience is whole, and we don't have superposed experiences, right? So we don't enter into these conscious superpositions, and this is sort of like the guiding principle kind of behind, the super-resistance model. Would you say that's like somewhat accurate? And
that's accurate for Eugene Wigner. If you look at Eugene Wigner's original paper, he says something like, if I'm observing my friend's in this laboratory, and I'm just going to assume that I'm the only one that causes the collapse. So what happens to my friend? Well, my friend would measure this quantum particle, just like in our example, and end up in this consciousness superposition because I haven't gone into the lab and measured my friend yet. And then Vigna says, but then my friend would be in this state of suspended animation, which is really getting at this idea of what could a superposition of consciousness even mean? Like, it doesn't seem that it's there in our introspection. It's not something we've sort of observed in any sense. So you might get the idea from that, and I think Vigna did, and this is what was motivating him, is that consciousness can't superpose. Well, then how are we going to fit it into the world? We can make it so that it's the cause of the collapse. I wouldn't want to put the point that strongly, partly because the many worlds interpretation of quantum mechanics does give us a way of thinking about consciousness superpositions. What happens is it's a bifurcation, a splitting of consciousness. We have two agents, and they have their own natural classical conscious experiences. That's the way to make sense of a superposition of consciousness. So, yeah, there is a way of making sense of consciousness superpositions. So I wouldn't want to argue that consciousness superpositions are incoherent. Therefore, we need something like consciousness being superposition-resistant. But, I mean, it's one of the guiding intuitions. I mean, I'm not trying to convince people that this theory is true. I'm completely agnostic on its truth. The motivation for developing it and working on it isn't because I think it's true. It's because I think it's fruitful. First and foremost, arguably, if we can resolve some of these issues about feedback in quantum computers, it's the most testable interpretation of quantum mechanics on offer, arguably. Let's start building the right type of system that can actually test it. I mean, that's the testability of it is one of the main things that attracts me to it. And also the fact that it combines two mathematical frameworks, quantum mechanics and integrated information theory. And I think that can be really interesting just for people working in quantum mechanics, looking at quantum integrated information theory and this new mathematical use of quantum theory. And then same with integrated information theory. People interested into the mathematics, people interested in generalizing it, should be interested in quantum integrated information theory. So just working on this theory, I mean, it can help build new sorts of experiments, make us think about new types of quantum circuits, but then on a more conceptual level, on a mathematical level, it gives us different ways of developing these mathematical frameworks, which can help us just understand them better. And then, obviously, there's a lot of philosophical interest as well. Who knows if it's true? But, probably it's not, right? But if it is true, that's going to be philosophopically significant. I mean, it looks like it's giving consciousness a fundamental role.
It's great to think about at the very least, yeah.
I mean, that's part of the hard problem of consciousness is what on earth does consciousness do? What's its function? What is its role? How does it physically affect things in the universe? And, well, this theory is giving us a proposal, a testable proposal. Consciousness can play a causal role through the collapse of the wave function.
It's been awesome talking. My final question to you, which I kind of have to ask, how does your collapse model compare to the orchestrated objective reduction model by Penrose and Hameroff? Maybe you could just give a little. This one does this, ours does this, and kind of pros and cons maybe here and there.
So the major difference is what causes collapse. So on our view, consciousness causes collapse on our model. On their model, consciousness does not cause collapse. On their model, gravity causes collapse. So once the superposition has reached a certain size, so that you've got a significant enough superposition of space-time, that's going to trigger the collapse. That's the OR, orchestrated reduction part of the OR model. So the collapse process has nothing to do, or at least in terms of what causes it, has nothing to do with consciousness. Whereas for us, consciousness has everything to do with the cause of the collapse. That's the biggest difference. Now, of course, they do have a theory of consciousness as well. That's the OR part of the OR model. But they seem to want to say that consciousness is identical to the collapses themselves. So once the gravity threshold has been met and you've got the collapse, well, then it's going to be like a constellation of collapses in the brain is going to constitute your conscious experience. And in order to explain the sorts of conscious experiences that we have, just collapse. Why would a given collapse give you a red experience versus a blue experience if it's just a collapse? So there's got to be something about what led up to the collapse that explains the quality of the experience and perhaps its quantity as well. And so that's where you get all this stuff about quantum computations in the brain, inside the microtubules. It's these quantum computations leading into the collapse that gives you the quality of consciousness from the collapse itself, as I understand the theory. And that raises very different issues from so there's a famous, well-known objection starting from Max Tegmark that's been developed by others, which is, well, we don't think these quantum computations can really happen in microtubules or really anywhere else in the brain due to decoherence. The brain is this warm, wet, mushy thing. It's interacting too heavily with its environment. There's no way that you can maintain this coherence in the brain. So that's a big concern for ORCOR. I guess whether they can answer that problem is an open question. That's not a problem for us, right? So we just don't at any point appeal to anything like quantum computations in the brain or anything like that. So this whole we don't have a decoherence problem.
Well, yeah, as long as you stick with like the classic IIT, right? Or is there a way to invoke quantum IIT and avoid those
so
concerns?
we do invoke quantum IIT. You have to invoke quantum IIT. You can't really do this with classical IIT. The reason why we don't have the decoherence problem is we're just not trying to say that the brain can maintain any complex quantum processes. There's no quantum computations. There need be no quantum computations going on in the brain for us. That's where you have the decoherence problem. For us, what's going on is there are these entanglements being set up between the environment and the brain. For example, when you look at your measuring device is in a quantum superposition of registering the particle as being here and registering it as being there, maybe on a screen. And then light reflects off that, enters your eye. Your eyes now enter into a quantum superposition of having information about the particle being here versus being there. That then enters into the brain. Well, then the neural correlates of consciousness will superpose. And that's all fine. But then that's going to create a superposition of consciousness. Consciousness resists superposition in this model. So that then collapses the brain, which collapses the eyes, collapses the whole system. There's nothing in there that you can't even state a decoherence problem. There's just nothing in that process that would even lead you to raise the problem in the first place. But in the ORCOR model, you need quantum computations being maintained for a non-negligible amount of time before the collapse happens to sort of color the collapse so that it gives you an actual quality of consciousness. That's what gets you into the decoherence problem.
And so you would say, like, in your model, you're just always collapse. Like, there is no like rate of collapse because there's no rate of needing to sustain any sort of quantum coherence. Like, these entanglement relations can be nearly instantaneous, or like the moment it becomes entangled, it gets reduced. Would that be accurate, or is there a time frame to your collapse?
You have to do it. Yeah, this is where it gets complicated. You have to do it at a time frame. So we distinguish two collapse models. One is absolute superposition resistance. The other is approximate superposition resistance. So absolute superposition resistance means consciousness cannot superpose. It's absolutely resistant to superposition. Cannot enter into superposition of distinct Q shapes. Once this process reaches the brain, there's no even little consciousness superposition. It just snaps, collapses immediately. So that would be nice if we could work with that. But that actually raises a very serious objection, a devastating objection, coming from the quantum Zeno effect.
Yeah.
The quantum Zeno effect tells us that if you continuously, strongly measure a quantum system, then you'll freeze it. So why does that come up here? Well, on our model, it's as if consciousness is being continuously measured, right? So if consciousness cannot superpose, it's as if consciousness itself is being continuously, strongly measured to keep it in a definite state of consciousness all the time. Okay, so that means, if you run through the usual argument for the quantum Zeno effect, that consciousness freezes. So, long story short, the absolute consciousness collapse model entails that consciousness never changes. It's frozen. Or it entails that it never evolved in the first place. Obviously empirically incorrect. You've got to avoid the quantum Zeno effect. You've got to allow a little...
Because you would just be frozen.
Right.
There'd be no movement possible.
Right. You've got to have a little bit of consciousness superposition. There has to be... It's got to take time for that collapse to fully occur. And so that's when, fortunately, the mathematics of this and collapse theories have already been developed, especially by Philip Pearl, the so-called continuous spontaneous localization model. So we adopt that. And so consciousness is not perfectly definite. There's a little bit of a superposition, and it takes a little bit of time for the collapse to happen. So there is that in the theory, and that's unavoidable.
All right. Well, it was great chatting with you, Kelvin. I'm really excited to see what you guys do next. It sounds like you're working with some quantum algorithms. Very excited to see where this will go. And I'll be looking forward to checking in the future again with you and getting some updates.
Absolutely. I enjoyed the discussion.
All right. Yeah. Thanks for being here. All right. So here we get into the sort of finale of the theory and some of my final comments here. So one thing that I found kind of confusing at the end of all of this is this simultaneous idea that the mind is somehow coming about through entanglement relationships in quantum bits, but then at the same time, there's no problem via decoherence. So to briefly reiterate this problem, decoherence is the idea that the brain is too warm, wet, and noisy, that you can't sustain quantum effects. Yes, this is true from our current understanding. However, with a deepening understanding of how biology works, there's really a growing field of quantum biology discovering that proteins might have these pockets where they can sustain quantum states that are, protected from the environment through molecular and biological mechanisms. So I don't think this is ruled out fundamentally that we can't have quantum effects in the brain. So that's kind of like an adjacent point. However, that argument is so ubiquitous in the consciousness field that you really can be shut down very quickly by provoking quantum consciousness, and people just say, hey, there's no quantum effects in the brain, and you go, oh, you're right, I'm out of here. So this is something that they're trying to avoid in their theory, right? So they're trying to say decoherence is not a problem because we're really just talking about quantum systems in the environment, and when they hit your brain, they get collapsed. So I can really understand this as a classical model where the brain has classical binary digital IIT, a quantum system comes in, it hits your conscious, digital components of your brain, and that collapses the photon or the wave function. But what's weird here is they're also saying that consciousness fundamentally collapses the wave function, implying that this is the fundamental process for all wave function collapse, that there is consciousness embedded panpsychically in the fabric of the universe. And so anytime you have a feedback loop between two quantum bits, you now have some phi property, some integration of quantum information, and then that starts collapsing the wave function, right? So the way that I can see this panning out for them is that there is some sort of substrate in the brain that enables macroscopic, large-scale quantum information processing, and that there's some sort of integration metric, and that integration metric is collapsing the wave function. And so they're not taking the leap to suggest that this is happening in the brain, but then it just kind of calls to question, okay, then what is the quantum IIT in the brain if it doesn't require large scale or sustained quantum effects? Could it happen instantaneously, which would have no, temporally extended effects? And then they said, no, there's like some continuous process of it emerging and collapsing. But you still just need entanglement in the brain, and you still need entanglement at a large enough scale to generate enough phi. This theory seems to me to be invoking large-scale quantum entanglement, and then how is this different from the Penrose-Hameroff model, for example? So in the Penrose-Hameroff model, the y-axis of the evolution of the quantum computer self is that there is this gravitational self-energy as the quantum computer evolves. So as these different, probability spaces or different mutually exclusive physical realities are splitting off, there's gravitational energy between the different physical realities in superposition. And once that reaches some threshold, then there is a collapse and it becomes self-measured. and that self-collapse results in some experience of consciousness, But is that y-axis of gravitational self-energy similar to the phi metric? Could you replace gravitational self-energy with phi in some way, right? Could the gravitational self-energy be equivalent to feedback loops or to entanglement relationships or to something? Is there some way to map between these two models, right? And then the other difference is that instead of having an instantaneous collapse, you'd have Schrodinger evolution, just like in the Penrose Hameroff model. And then instead of being instantaneous, you just take that instantaneousness and maybe you smear it out a little bit, make it continuous. You kind of have this rhythmic trade-off between the two. Is there a more complicated dynamic where the measurement happens very quickly and Schrodinger evolution happens more slowly? Then we're just getting approximately closer to the Penrose Hameroff model. And, how different are they really? But what's really interesting is that we live in this era, historical, freeze frame right now, where the Penrose Hameroff model is just considered debunked. It's considered, fringe in some way. And I feel like, to what degree is this a reinventing or a reimagining of the self-collapse model, and how different are they really, Do we need to rigorously compare the two, and can we really get away with skirting around the decoherence problem, which the Penrose Hameroff model is tackling head on, right? A lot of Stuart's work right now is trying to look at molecular mechanisms for creating large-scale, temporally coherent quantum effects, and yet this other model is diving into the mathematics potentially, or looking at quantum algorithms, also equally important. So I really applaud Kelvin and David Chalmers for really diving into this quantum consciousness problem and taking the measurement problem seriously and trying to put consciousness in this equation. And I'm really excited to see where this goes and what comes of this. It's early days with this new push here, but I really like the idea of self-collapse, of consciousness relating to this collapse process. So we'll see where this gets us, and look forward to talking more.